Welcome, everybody. We will be talking about continuity. Um, we have seen that a polynomial function f satisfies the equation that the limit of f of x as x goes to c is equal to f of c. So if f is a polynomial function, then we know that the limit of f as x approaches c is equal to f of c. That is the limit of the function f at c agrees with the value of the function at c. So this equation is satisfied by any given polynomial function. So any other function, any function that satisfies this equation is called continuous at the point x is equal to c. So we say that a function f is continuous at x is equal to c if all three of the following hold. Number one, f of c is defined, that is, f is defined at c, and in other words, c is in the domain of f. Number two, the limit of f as x approaches c exists, and number three, that the limit of f at c is equal to the value of the function f at c. So the limit of f at c is equal to f of c. If these three conditions hold, then we say that f is continuous at c. If any one of the three conditions here doesn't hold, then we say that f is discontinuous when x is equal to c. We say that a function is continuous on the open interval ab if it is continuous at each number in the interval. Here is an example. Let's say, let's look at the function f of x is equal to x plus 1, and the function g of x is equal to x squared minus 1 over x minus 1. And we're going to compare these two functions. This is the graph of the function f, and this is the point 1, 2. So f of 1, you can see that f of 1 is equal to 2. And here is the graph of the function g of x. And you can see that g of x is undefined at 1. So notice that we have done similar things before. So here the function g of x, if I factor out the numerator, I get x minus 1, x plus 1 over x minus 1, which is equal to x plus 1 if x is not equal to 1. So what we see is that the function g of x is exactly the same as the function f of x for all values of x except when x is 1. In other words, g and f, they have the same exact graph. The only difference is the point 1, 2 lies on the graph of f, and the point 1, 2 does not lie on the graph of g. So now if you look at the limit of f at 1, you see that that limit is 2, and 2 is the value of f at 1. So since the limit of since f is defined at 1 and the limit of f exists at 1 and they are equal, we see that f is continuous at x is equal to 1. On the other hand, if you look at the function g of x, the limit of g of x at 1 exists and is equal to 2. However, g of 1 is undefined, so therefore g is not continuous, which we also say that g is discontinuous at x is equal to 1. Notice that f is continuous for all x, and g is continuous G is continuous everywhere except at 1. So one way to express that is that we say that G is continuous on the set of numbers r slash negative 1 here. So this is like a set minus, that is, from the set of all real numbers we get rid of negative 1. So that's the set here. So G is continuous at all points except at 1. So it's continuous on R minus the set with the single point negative 1. F is continuous everywhere. So F is actually continuous on the set of all real numbers R. In this case, for G, in interval notation, what we would be writing is the following. We will be writing that G is continuous on the interval from negative infinity to 1, union 1 to infinity. Notice the open parenthesis at 1. So what that means is the 1 is not included in either of the two intervals here. So this is a set of all real numbers except 1. Okay, so I see that I said something wrong here. This shouldn't be a negative 1. This should be a positive 1. So G is discontinuous at 1, and I mistakenly wrote negative 1 here. So this should be a positive 1 here. Okay, so I will stop the video here. In the next video, we will be looking at an exercise.